In 1988, Aloha Airlines Flight 243 suffered a catastrophic explosive decompression at 24,000 feet. This wasn't a failure of simple physical wear. The structural degradation was caused by multi-site corrosion fatigue, originating inside the rivet lap joints of the fuselage skin. The aircraft was built with AA2024, a high-strength aluminum alloy. To achieve its mechanical properties, the alloy relies on copper-rich intermetallic precipitates distributed throughout the metal. Looking at the bare metal substrate reveals a crystalline microstructure where these copper precipitates are suspended within the aluminum matrix. This creates an electrochemical contradiction. Within the alloy, these copper precipitates act as localized cathodes relative to the surrounding aluminum matrix. When moisture or marine chlorides introduce an electrolyte, it completes a microgalvanic cell. The aluminum matrix is eaten away through pitting corrosion. The alloying elements that provide structural strength are the same elements that create a specific electrochemical vulnerability when exposed to atmospheric conditions. For 80 years, the industry suppressed this microgalvanic destruction with chromate conversion coatings, treatments based on hexavanic chromium. Chromates provide active repassivation. They release ions that migrate across the metal surface to protect newly exposed or damaged areas. Modern REACH and ROSH mandates are now banning hexavalent chromium due to its toxicity and carcinogenic properties. Standard anodizing cannot solve this. Traditional oxide growth creates microcracks directly over the copper precipitates, leaving high-strength alloys unprotected. The solution requires moving beyond passive chemistry to architect a multi-layered hybrid electroceramic stack built from first principles. To succeed, this hybrid architecture must replicate the robust physical barrier and the active chemical defense of legacy chromates without the use of hazardous chemicals. Building the new architecture starts by immersing the bare AA2024 substrate in an alkaline silicate electrolyte. As the voltage increases during oxidation, it reaches the U5 threshold, the point where the dielectric properties of the oxide layer break down. Micro-arc oxidation intentionally pushes past this limit to weaponize this breakdown. Entering this plasma regime generates microscopic electrical discharges across the metal surface, reaching temperatures between 3,000 and 10,000 Kelvin. These thermal discharges locally melt the aluminum, forcing it to react with the electrolyte before it rapidly solidifies. This process grows a thick ceramic layer composed of alpha and gamma alumina, reaching a hardness of nearly 1,800 Vickers. MAO overcomes the failure modes of standard anodizing by using plasma discharges to drive the uniform growth of a metallurgically bonded ceramic layer. While the MAO process creates a hard barrier, the plasma dynamics leave behind an inherently porous, cratered morphology. The resulting ceramic surface is characterized by microscopic mud cracking and a pancake-like structure. This porosity is a critical flaw. Corrosive chloride ions can travel straight down these open vertical channels to reach the bare aluminum substrate. Solving this requires sealing the porous oxide structure with a complementary polymer matrix. A chemical-resistant epoxy phenol novolac resin is applied via dip coating. The liquid epoxy flows into the craters and mud cracks, structurally interlocking with the ceramic skeleton before solidifying into a tight bond. The epoxy fills the macroporosity, but a bare polymer remains too permeable at the molecular level to survive a 30-year service life on its own. The final layer of the architecture embeds a 3% weight dispersion of ceramic nanoparticles directly into the epoxy matrix. To optimize the nanocomposite, the formulation uses 1 part zinc oxide to 2 parts cerium oxide. The zinc oxide nanoparticles serve to densify the polymer matrix, acting as highly dispersed physical obstacles against invading elements. This creates a tortuous path, preventing electrolytes from traveling in a straight line toward the metal. While this slows down diffusion, it cannot replicate the active healing properties of chromates if an ion eventually breaches the barrier. This is why cerium oxide is added as a localized chemical inhibitor. When the coating is damaged or aggressive electrolytes penetrate, cerium ions are released and migrate to the site of the defect. These ions form an insoluble passivating weighting over the defect, blocking the oxygen reduction reaction and halting corrosion. Every layer has a purpose. The MAO ceramic is the skeleton, the epoxy is the seal. Zinc oxide builds the physical maze. Cerium oxide provides chemical reinforcement. We verify the efficacy of this hybrid stack using electrochemical impedance spectroscopy. The quantitative metric for protection is charge transfer resistance, measured in ohms. The legacy toxic standard, chromate conversion coating, provides resistance in the 10 to the 4th to 10 to the 5th ohms range. Standard sealed anodizing performs slightly better, reaching 10 to the 6th ohms. The charge transfer resistance of the hybrid stack reaches 1.11 times 10 to the 7th ohms. This engineered system matches legacy standards and outperforms traditional aerospace protections by 2 orders of magnitude. Beyond the electrochemical data, this system translates to the manufacturing floor. This dip coating process is industrially scalable and operates at low temperatures, ensuring the heat treatment state of the airframe remains unchanged. These laboratory results strongly indicate decades of structural stability for the airframe, even under extreme thermal cycling and relentless marine exposure. Moving away from hazardous chemicals is a necessary evolution for the industry, solving the microgalvanic paradox through active plasma physics and engineered nanocomposites.